Hi everyone, this is going to be the video about the definition of limits and definition of a continuity of a one variable function. And the main purpose of this lecture is about give you enough motivation about why the definition of the continuity of a function is defined that way, and give you a slightly different approach to the definition of the continuity that I think to most students is I find, especially for the first year calculus students, it might sound a little bit more reasonable and make sense than so-called this epsilon delta definition, but it is still mathematically correct approach. First, let me mention about this slope of tangent lines. I'm not going to go through the lengthy introduction to the definition of a slope of tangent lines, but let me briefly mention here that slope of the tangent line. This second picture here is called a tangent line. The quality of this red line touching this curve locally is called the tangency, and to mathematically define this quality of intersection locally just around here, not about what this line is doing to the other part of the curve, just about here, is defined, the tangency is defined in the following way. If P is fixed, the same P is here, if Q is approached along this line, and you can think of along this curve, excuse me, if you can think of a line that passes through these 2 points, and that line is called a secant line, and you can see the way this red line intersects this point P is not the quite same as this one. So again, it's not quite precise definition, but as Q is approaching very, very, very close to this P, but never being equal to each other, equal to P, then it almost becomes this red line. So to make this idea more precise and make the idea more precise in mathematics, they needed the following concept, which is this concept of limits. And I forgot to mention this part right here called instantaneous rate of change. This is more geometric description of what they were doing, but in physics, this rises from the notion of instantaneous rate of change, such as instantaneous speed, instantaneous change of speed, which is instantaneous acceleration. For that, this concept of limit rises, namely the point Q is very, very, very close to P. That kind of thing is the idea of a concept of limit. And in most calculus textbook, after this concept of limits, what they introduce is this concept of continuity. They use this concept of limit to define the concept of continuity, and then give a more mathematically correct approach to the slope of a tangent line. So although it started from here, they have to backtrack and then kind of create this notion of concept of limits and give a better foundation of this slope of tangent line or instantaneous rate of change, and this notion of a continuity. This lecture is mainly focused on this notion of continuity and the concept of limits. So let me first explain about the continuity. This notion of continuity may rise nicely from when we think about space, distance between the two positions, or time. To me, the time is most natural notion that where we accept there's something called continuity. No matter what that is, you can also think about this type of pencil drawing, that you never lift your pencil and it's continuously drawing. So we do use this type of notion, continuity, in our everyday lives. Somewhat we are comfortable with that notion. For mathematicians, it became tricky, and they wanted to give a slightly different approach because that notion it turned out as tricky to define. So that's why they begin to use this. They decided to use this concept of limits. Maybe the single most important my motivation to make this video is the following: defining these limits, which we will use to define the concept of continuity. that we're going to define the limits without using concept of continuity anywhere. And when we establish the facts about the limits, and we will try to avoid using the property of the continuity. So later we can establish the property of continuity using the property of the limits. So that bear it in your mind that we're about to enter the defining these limits without using the concepts of or property of continuity. First, we will define the meaning of a sequence of numbers approaching a number. This example may look very natural, and then you might agree what we mean by approaching a number. So here's an example. A sequence is usually denoted like this, and x subscript n, like this here. The first number is 1, and second number is 1/2, and third number is 1/3, and fourth number is supposed to be 1/4, and the nth number here is going to be 1/n. So by writing this general formula of nth term of the sequence, like this 1/n, we described this sequence of infinitely many numbers. When we are about to prove something or establish some fact, we can use all sorts of idea and inspiration and here and there, but from there we get an idea and the property that we think is true. But when we prove those things, you have to go through the rigorous logic. But we can always think about these things and the pictures and whatever that helps us to understand the situation first. So if you put these numbers on the number line, it looks like this. 1 is here. Here 0 is not part of this sequence, but this is, since it turned out this is where the sequence is heading, approaching, so I put it there. But the second number is 1/3, and third number is 1/2, and third number is 1/3, fourth number is 1/4. It seems like it's getting closer and closer to 0. So in everyday language, getting closer and closer, it's kind of a vague meaning. For example, as we get closer and closer to 0, you might agree that it will never actually pass this 0. And think about there's -1 over here, and one can say these sequence of numbers is getting closer and closer to -1 as well. And so it's also getting closer and closer to -2 as well. So when we say it's getting closer to -0 and closer to 0, it should be a little bit more, needs to be specified. So that's what we are about to do. It's not getting closer, the distance is not just a decreasing, it's really what we think is getting closer and closer, and then that's what we are about to define. That is one example, but the second example is really important, and the second example really motivates the definition of the limit the way it is defined in mathematics. Since the behavior is a bit complicated, I will just describe in words and I'm not writing down everything. So we have same kind of numbers we're dealing with, 1 and 1/2 and 1/3 and 1/4, but we're going to have a little bit erratic looking behavior. We're going to start from 1, and the next number is 1/2, and the next number is 1/3. That looks about right. But when we hit this 1/100th, we're going to go back all the way to the 1/2 right here and repeat exactly the same thing. Then it's a 1/3 and 1/4 and so on. This time, second time we're approaching the 0, we're going to wait until when we hit 1,000th. When we hit 1,000th, we come back just like the second red position there. We'll come back to 1/3, then go all the way down to until we hit this 10,000th, and then we come back all the way and come back to the 1/4, and then 1/5, and 1/6, and so on. So if you keep repeating this pattern, I hope you got this idea of this approaching. Mathematicians like to call this one also eventually approaches 0. That's the key word there, eventually approaches 0. So in their definition of a sequence of numbers approaching a number, a, for example, in this case, a 0, they'd like to include this case as well. Not just, we so-called the monotone approach, either just continuously decreasing or continuously increasing, not continuously, that's not, it's just a decreasing and increasing, or not just those, we'd like to include this type of complicated behavior. But if we understand, if it's eventually getting closer and closer to 0, we'd like to include that as a sequence that is approaching some number as well. So these two examples are the main important example. I wasn't very efficient in making the slides, and I forgot to show this portion there, but I think I already explained in 100 first, and we come back to this 1/2, and then we go back to 102 then, and I explained that what we really wanted to describe in our precise mathematical definition of limits, and what we wanted to do is eventual approach, right? Eventually approach to 0. So those are the two things I meant to show, and which I didn't. So I wrote it here. There's two things in that word, approach. So getting closer and closer to A. Again, this is not very precise. We're not just heading toward to A. We're really, the distance, for example, the terms of this sequence of number to A, that number is becoming almost 0. And eventually, I hope you understand this term, but right now, if you don't know how to describe it, and the following is mathematicians' attempt to get this eventual property taken care of. So this is how they do it in eventual. So here is the target point. We think that, for example, we think the sequence is approaching eventually. So what they do is that they decide to put an interval centered at this number A, and to the right go the 1/2 units, and to the left you go 1/2 unit, which are written here A minus 1/2, then A plus 1/2. So A is here. So to the right, the coordinate here will be this 1/2 plus A, and coordinate there will be A minus 1/2. So we decided to put how many terms are in here. So if you look at just the radius of this 1/2 interval, to see which terms fall in the small interval. So if it is 1/2, it's quite close to A. So it turns out, for example, A99 is outside the interval, but A100 came inside, and A101 came inside, and for some mathematical trick they were able to establish that after this point, the 100th point, every term is going to be in there. That means it's infinitely many terms. Suppose we could argue that. So that's nice. It seems like these terms are very, very close to A. So you can see probably that's not enough. If they can all gather around just right around that point, not really A. So to establish this A, we have to kind of be able to do the following, forever and ever. So here, in this one, I made a smaller interval. Let's say that was actually 1/4 interval. So A is here. To the right, you go 1/4 unit, and to the left, we go 1/4 unit. So let's imagine that if we squeeze this the radius around this A smaller like this, maybe we eliminated 100. 100th term, A100th, is no longer there anymore. So they investigated, went into 101 and 200 and go all the way up to 300. Turns out, in the 500th term, they begin to fall in here. And again, mathematically, they could argue that, let's suppose, that term after this 500th term, everything fall inside this interval. Suppose that was the case. Then again, this is not enough, and then they decided to, okay, why don't we do a lot smaller, like 1/10th interval. So what kind of terms fall in here? Maybe there are lots of outliers here, but after the 1000th term, they say, and 1001st term, everything, they could argue that they fall in here. So they wanted to define it this way: no matter how smaller interval you put it in there will be some index out there, let's say 2 million or 2 zillion, whatever. However that index, however big, how big that index is, since from that index, if we could show all those ANs are contained, fall inside this tiny interval, and if we can establish that fact for arbitrarily small interval around that A, and that is our definition. So of the limit of a sequence of numbers approaching an A. So let me write down that term more mathematically precisely. So here's the definition. So we'd like to establish the fact that a sequence of number xn approaches A as our index approaches infinity. So that's the notation, and that's the eventually approaching A notation, and following property must be must be true. Given epsilon, this is the radius 1/2, 1/4, and 1/10 that I was talking about. So it's given, arbitrarily given epsilon is usually given by epsilon. In not actual example, we have to deal with this epsilon to establish the fact, this arbitrarily small quantity. There is this index. These were 100th and 500th and 1000th term that I was talking about. And this depends on epsilon, just like we did before. If it is 1/2, it starts from 100. If it is 1/4, it may start from 500 and stuff like that. So given small radius around this A in target A, there's like A plus epsilon, A minus epsilon, there's usually this large index such that all the terms AN fall within this interval, A plus epsilon and A minus epsilon. All the terms is in between here, as long as the index exceed this number n that we could find. So to establish this fact, what we should do is, given this letter epsilon, we're not going to make this into a number usually. It's going to be just a letter epsilon. And then we have to figure out n in terms of epsilon, just like usually formula, like 2 times 1 over epsilon or 1 over epsilon squared and something like that, such that we have to argue this index is greater than n that we figured out. This all the an must be in between this. In establishing this inequality, the challenge is that not using the continuity of the operation involved in that. You have to strictly use algebraic property and the inequality that comes with it. So this is the definition. Let me read it again. Given epsilon, positive number epsilon, there is n depending on that epsilon, such that all the terms fall in between A minus epsilon and A plus epsilon if the index n is greater than the capital index, the capital N. So that's the eventual part is taken care of here. Approaching part is taken care of this arbitrary property of epsilon. Okay, so I wrote here the definition again, and we're about to do some example to understand this definition a little bit and how to handle this definition a little bit. But I want you to keep in mind that we're going to be using this definition, this very mathematically precise definition, to take care of the continuity, and we will be using this to establish the property of the continuity. So when we establish the facts about the a sequence approaching something, we have to do our best to avoid use the property of the continuity, which is kind of embedded or internalized in our mind. Whoever trained enough with mathematics, this something is natural to assume, but we have to kind of distinguish that, and that's the challenge. We have to extract that part out of our argument, and that's the challenge of the following exercise. So this is not quite introduced, the following is not quite introduced in this way, but after myself, when I learned this for the first time, and this I find it's very important to introduce it in this way. So there's this fundamental lemma that everywhere when we use this establish continuity or the so-called convergence of the sequence approaching something, everything is kind of boils down to the following situation. So we reduce most of the problem to the following situation. And therefore, we need to at least establish this fact, these two facts, which I call lemma, fundamental lemma in the proving facts about limits. This one needs to be very rigorously proved. It's just strictly following the definition of the limit we just defined. So this will be pretty strict statement. After that, using this lemma, it's a lot better and it's a lot more intuitive, and still you're not using any of the continuity property. It will be nicer. But this one, for this two statement, you have to bear with me and try to follow the mathematician's approach, rigorous approach, for this following two facts. So here's the first bit of the proof, and if you still don't quite feel comfortable with the definition of the limits, I want you to stop the video and go back and review just one more time before we enter the proof of the item number 1, which is here. So what's given is that suppose we're given that this an is one sequence and another sequence both approach 0. Since we know they approach 0, and we have the property that is given, stated in the definition of limit approaching something. So since an approaches 0, no matter what you give to that radius around that the convergence point 0, which was capital A before. Now, this is small radius around that capital A. I'm sorry. So epsilon 1, we don't know what that is, but if it is whatever that is, there will be some index. So eventually, if an has the index greater than that giant index n1 usually, all those the terms fall in between 0 plus epsilon 1 and 0 minus epsilon 1. That 0 came from that target right there. It's approaching. If you think about it, the statement is going to be exactly parallel with the Bn. It's just a different sequence that approaches in a different fashion, approaching A in different fashion. So given whatever the number we have, epsilon 2, which is usually a small number, there will be some giant index, n2. As long as our index for Bn is greater than index n2, those Bn will fall in between 0 minus epsilon 1 and 0 plus epsilon 2. Sorry, this is typo. This is supposed to be epsilon 2. And that 0 came from where Bn is approaching. So again, the tricky part to understand it here is this epsilon 1 and epsilon 2 is free. You can give any number. Then depending on that values of epsilon 1 and epsilon 2 you choose, there will be this epsilon n1 and n2, and these number will fall in between here. So we're going to carefully control these two things to get what we want. Think about what we want is this. We want to show an plus bn approaching 0. If you assume the continuity of this operation addition, this seems like a silly, obvious, true statement if you want a geometrical view, but that's not what we're doing. We want to get rid of that, our comfortable notion of continuity, out of our argument and then strictly follow the definition. So what we have to establish is, let me actually show you if I can. I'm going to go through the slides quickly. Okay, it didn't fit in, so I have to explain it here. So this is the target, and think about the definition of the convergence of a sequence again. Given an epsilon, we have to find some index such that this an plus bn fall in between 0 plus epsilon and 0 minus epsilon. That's what we need to show. So why we're setting this epsilon 1 and epsilon 2 like this may not be too clear at the moment, but let's see. This is one of the things that if you just follow through, not really understanding why they're setting them equal to each other, and just focusing on how the how to go from one step to the next step after that, and then how they fit together, seeing how they fit together, you might understand why they set things like that. So there's some logical gap, and it is not incorrect. It's a correct statement. You can always set epsilon 1 and epsilon 2 to anything. It is not clear at the moment why they're setting the epsilon 1 and epsilon 2 like that. So for that one that I'm not quite answering nicely, because it's going to be quite confusing if I give a lengthy explanation here. So try to understand there's nothing wrong with this two-step. Epsilon is going to be some arbitrary positive number. Since epsilon 1 and epsilon 2 can be anything it can be, just like this one, so we're setting these two numbers to be the half of these epsilons given and half of this epsilons given. There's nothing's wrong with that step. It's unclear why they're doing it, but nothing's wrong, right? If nothing's wrong here, the proof is correct. All right, let's understand the motivation of the values of epsilon 1 and epsilon 2 later. Just understand this is allowed. Okay, since this epsilon 1 is given, and there will be this n1, because an approaches 0, and with that property. So as long as our index n is greater than n1, our an will fall in between epsilon 1 and negative epsilon 1. But epsilon 1 is half of the epsilon and half of the negative epsilon right there. So we have this property of an. And since we have epsilon 2, we have the same property for bn. So if our index is greater than n2, which is depending on our choice of epsilon 2, which is really controlled by epsilon, therefore this n2 is depending on epsilon. No matter what your m is, as long as it's greater than n2, then bm will fall in between epsilon 2 and negative epsilon 2. But epsilon 2 is 1/2. So there is a 1/2 epsilon. Epsilon 2 is a 1/2 epsilon. Therefore, there's a 1/2 epsilon there and negative 1/2 epsilon there. So we get this property, well, no matter what you have for epsilon 1 and epsilon 2. Okay, so using the property an and bn, both are approaching 0, we have carefully controlled the how this an it fit in and how this bm is fit in. So how do we go from here to the property of that an plus bn is using both properties. To use both properties, we need to have this both condition. So we want an index that is greater than n1 and greater than n2, so that we have this both property. And from there, we can kind of cook up this an plus bn. So how can we satisfy that kind of condition? Something must be greater than 1, something must be greater than 2. So that's pretty much it, but in mathematical notation, that would be like this. Why don't we put this bound for the index like this, maximum of n1 and n2. And then if some index is greater than this capital N, and then it is going to be greater than n1 and greater than n2, whatever that is greater than n2 or greater than n1, whichever one is a larger number, that's what this maximum is. So for example, if n1 is 200, if n2 is 300, then this one will be 300. If this is 5,000, n1 is 5,000, and n2 is 2,000, then n1 will be bigger than n2. So the maximum of n1 and n2 will be that n1. So that's the index. So if we have an index greater than n1, it is greater than n1, and greater than if it's greater than maximum of n1 and n2, excuse me, then it's going to be greater than n1, and it's going to be greater than n2. So I put it here, and so that we can do something down there. So it's summarized, just what we just talked about, and then listed is summarized here. Then let's pick a index n that is greater than plain n, which is in turn greater than equal to n1 or n2. So if we pick an index there, that is automatically greater than n1 and greater than n2 because of this choice of capital N. So we have for that same index and n here, both satisfied, we have property of an fit in between half epsilon and negative half epsilon, and for bn has half epsilon and negative half epsilon. So here's the point that we can explain the why they chose 1/2 epsilon. So again, from going from given positive epsilon to the next part, it's not wrong, it's absolutely correct. You can choose any epsilon 1 and epsilon 2, but it was unclear that why they're doing this, and I'm about to explain it here. So if you choose these free epsilon 1 and epsilon 2 like this, and then you try to add this an and bn, which is what we want to show here. And if you add these two quantities side by side, which is allowed, it does not use any continuity, it only uses the simple inequality fact. If you add this an and bn, you end up adding these two things side by side. If you're subtracting these two, if you're multiplying these two, it's very tricky and different. It only works for addition, and that has to be rigorously thought out. But I'd like to claim that it does not use continuity at all. It's just about using simple facts about inequality. So if you add these two side by side, then you have one full copy of epsilon and another -1 and one full copy of epsilon there, so that you end up at clean statement like this. an plus bn is in between epsilon and negative epsilon. If you just neglect this treatment, it's often you end up at the end using the argument or the property of the continuity if you were being sloppy about treating this carefully. So that's the deal. They want it to be carefully controlled, this balance like that, and at the end you have a clean statement from that beginning. We have epsilon, an plus bn fall in epsilon and negative epsilon. And here, without using any continuity of this boundary condition, we just simply added and it became epsilon. So again, if these two things, all these things that sounds too technical to you, what you have to focus on is that re-examine roughly and understand there is no part we uses the property of a continuity in there, and strictly just following the definition of the limits, we're able to establish that given any epsilon, using the fact that an and bn individually approach 0, given epsilon, we could show that eventually an plus bn fall in between epsilon and negative epsilon forever. So that is the end of the proof of the item number 1 there. Item number 2, it goes a lot like that, and then I wish I could go probably I can go a little bit faster, but it's very similar. But I'd like to give a rigorous proof, and we will be relying on these two facts for the rest of the part and easier. So beginning of the proof of second property, that we have this property again, an approaching 0. So no matter what epsilon 1 is given, there will be some large index such that as long as we have an index larger than that, all the forever from that point on, this an will fall in epsilon 1, negative epsilon 1, and nothing will escape that. No term will escape that boundary. Epsilon 1 and negative epsilon 1. So again, what we want to show is a Cn approaching 0. So we start from epsilon, and we're choosing this weird epsilon 1 again. But again, I want you to focus on this argument that whether it's correct or not, nothing is wrong with it. Epsilon 1, plain epsilon, positive is given, and epsilon 1 can be anything, but this choice will make our argument nice and pretty. So epsilon 1 we will choose epsilon divided by absolute value of c. As long as c is non-zero, this is allowed. So nothing is wrong with that step. So let's keep that in mind and not questioning why the epsilon has to be that. What epsilon 1 can be free. So this is all right. So let's think about what this n1 is. Before we had to choose this maximum of something, it's because we had these two sequences, and here we essentially just dealing with the one sequence. So that's why we're just dealing with n1. It turns out if we have n greater than n1, that what's given here, it'll work. So if n is greater than n1, we have this property that an will be in between epsilon 1 and negative epsilon 1, no matter what that epsilon 1 was. So, but we chose epsilon 1 to be this following quantity, epsilon divided by absolute value of c, so negative part here. So since c is absolute value of c is a positive number, and multiplying both sides by this positive number will preserve the direction of this inequality. So it looks like this. Okay? And because of the symmetry of epsilon and negative epsilon there, whether c is a positive or negative, it'll be always like this. So we can even lose that absolute value after we multiply that positive number. So this is true. So given epsilon, there is this n1 which came from the property that an is approaching 0. Then we showed that c times an is in between epsilon and negative epsilon. If you think about it, that's exactly the definition of the limit approaching 0. So we have proved these two fundamental facts. And using these two fundamental facts, and we're going to use other properties of limits and a continuity relying on this fact. And then from that on, you don't have to deal with that epsilon thing again. So that's why I think I approach it this way. So first, these two fundamental facts, we use this epsilon thing, but since then, we don't have to. After that, we don't have to use the epsilon definition again. We keep using this definition. Let me remind you again about the purpose of the video. This video is mainly to give you the mathematician's approach to define the continuity of a function without using the continuity in it. And especially, we do that using in terms of a limit. And then I focused on how the limit is dealt by mathematicians. And in example, I try to show that how we establish some of the facts about the limits of a sequence of numbers without using the concept of a limit. And that's important. We need to see that how these things can be possibly done without using the property of continuity. Now we're about to enter this function again. So this is the main goal, actually. The limit was a preparation for that. So when we say f of x approaches a as x approaches a, which is written here, what we have to focus on is this whole definition. The point of this definition is to clarify the meaning of x approaches a, and this will be used to define the continuity of a function. So we don't want to use the continuity in this part, x approaches a. So if x approaches a, not continuously, what do we mean by x approaches a? And we use sequence here like this. So if we have a sequence that approaches a, whenever that happens, this associated sequence f of xn, f of x is a number, and this forms another sequence. This sequence is supposed to approach a number, which is common for every time we choose a different sequence that approaches little a. This little a is fixed, that doesn't change, but you can imagine there are lots of infinitely many different ways to approach a. Not from left or right. That's another misconcept in the calculus instruction. Those are not the only two options. If you remember, there are many different ways to approach an a. So let me show you here what those. So here, this movement is not continuous movement. It is suppose say our x1 is here, and x2 is there, and x3 is there. Now x4 is very, very close to a, and then you can think of any erratic behavior of this xn, but maybe it eventually approaches a. So following that definition of a limit approaching a number a, as we defined earlier. And I just pretend some more complicated erratic behavior of xn that approaches this number a. So that's what we mean by xn approaches a, not just from the left or right, or especially not continuously at all, along a sequence. As this xn hopping around crazy like this, but eventually approach a, what's going to happen to f of xn and f of xn over there? If they're all, no matter how you jumping around and eventually approach a, if in all the cases if f of xn approaches the same number all the time, if that happened to be the case, then we say f of x approaches a as x approaches a, right? So because we're using this sequence, there is no continuity involved in approaching anything. And whenever this happens, we abbreviate all this thing with this notation, that limit x approaches a, f of x approaches a, is uses the equal symbol, not arrow, whenever there's this limit part is. And the whole point of this lengthy discussion is to clarify the meaning of x approaches a, not from the left or right, but along arbitrary sequence to a fixed number. Sequence approaching a fixed number a. So with this definition, we're very close to now define the continuity of a function. That's the whole kind of point of this lecture. But first, let's, I think I mentioned this earlier, the idea, the everyday notion of a continuity is like this pencil drawing. Start from here and keep drawing the pencil like this, and then what we see to human eyes, the quality of these marks is called continuous. And another thing I'd like to point out, this is a whole thing. It is not just one position. This whole thing looks like continuous to us. So that kind of property in mathematics is called a global property. This whole object, not just at one point, right? That whole object is called continuous. To accomplish that, often mathematicians have to look at actually locally. So put some property in each point, and which is going to be a local property. And then if it is happening everywhere, we decide, we define that to be a continuous. So here's the first local attempt. We are looking at one point, not all the curve, just one point right here. And at x equals a, then function value will be f of a. And we say f is continuous at a if the following happens. The left-hand side is the limit x approaches a f of x, which is discussed here. As x approaches and hopping around to a, what's going to happen to f of x values around it here? If they always approaches this function value at their f of a, if that happens, then that's the meaning of a f being continuous at a. It's quite a reasonable approach. The behavior, the values of the behavior around x equals a, in here and there. The behavior is exactly kind of around that point f of a, and we call this a continuous. But this is not the continuity that I was talking about here. This is a continuity at one point. If this happens everywhere here in whatever the point you choose, the function value around that given point is very, very close to the function value assigned that precise point x equals a. If that happened, is continuous. If that properties happen everywhere, every point in AB, f is continuous at every point in that interval. AB here, start from A there and start from B. It's not that arbitrary A here, it's a different A. Then we say the function is continuous or on A and B. And we think that captures the property that we were talking about here, which wasn't that precise. So this is the global property, and that is the local. So if we have all the local things satisfied, we'd like to say that's a globally continuous. This is mathematicians' attempts to define that continuity over there. Whenever we pass from local property to global property, something weird can happen. And from my experience of looking at many different mathematical subjects, I often see this is a common theme, and they want to investigate what is happening from the local property to the global property. And indeed, in around 1800, and functions, so-called nowhere differentiable function, is continuous everywhere, that like we had talked about here, but it's not differentiable anywhere. That kind of function kind of surprised the whole community about the consequence of what we have defined can include some really wild picture of something that we shouldn't call as continuous, but it falls in and satisfied all the definitions of continuity. So to sum up, although this is our best attempt to describe that kind of nice continuous motion, it happened to include some very wild nature of a graph, so-called fractal. Before I move on to the next part, let me clarify this very concise statement there. It has two parts. The limit x approaches a f of x exists to be, let's say, capital A, that value of capital A happen to be equal to f of a, which is just a function value assigned. Often when students work this problem out, when they do examples, they often don't distinguish these two things, because the first example they encounter is basically just using this property to do something, so they think it is just basically the same thing. But that is the biggest misconception when they're learning this continuity, and it is very difficult for instructors to kind of clarify that these two things are different things, and if it is what is happening around that point A right here and there, doesn't have to be exactly this value. And whenever we are using this property, you are assuming this is continuity, and whenever you have to establish this fact, not using that continuity can be quite puzzling. And then you will come back to here and really think about and kind of clear up your logic and correctly line up your argument and all correct reasoning, and then hope this type of thing that I'm doing is going to help you. But it's difficult to distinguish these two things. It's all kind of internalized in our thinking. So here I collected the very definition of f of x approaches a as x approaches a, and the continuity at a point. And if this happens everywhere at every point in an interval, we have a global continuity. But what's stated here is a local continuity. But often we deal with that property in the problem, so I summarized it here again. So I chose this example because I hope you remember that example, the fundamental lemmas that says an plus bn approaches 0. If an approaches 0 and bn approaches 0. And I was saying that we're going through the rigorous way of proving that because we don't want to use the continuity of the plus property right there. Okay, so here, using that lemma, we're going to actually establish the two functions continuous, and if you add them up, and it becomes a continuous function. So to many of you, this is kind of obvious property, and if you're good at physics and use mathematics a lot, and these type of property internalize in you, then not really thinking about how to extract what is your correct reasonings are and so on. Here's an approach, and we're going to be using the sequences, and that's the trick that I'm pulling in here. Rather than using epsilon and delta, we use that. Everything goes into that proof of a lemma, and here it is. Okay, I wrote here something I have to examine before I, announce something. But here little picture I didn't plan to explain, but here it is. And to whom, if this continuity property is obvious, then what you're really thinking is that f of x here is represented into that direction, and g of x is length is represented into that direction. If both are positive, for example, then and the continuity seems like it's kind of obvious. G of x is continuously going to that direction and continuously going to that direction. So the value will be continuously changing or something like that. So, but what we are doing here is not just messing things around like this. We're trying to be, a little bit more rigorous in our reasoning. So we don't use continuity to prove continuities. F of x and g of x are continuous, but the deal is that here we're trying to sort of prove that this plus operation is continuous. That's what we're trying to prove it, and you can't assume that's what we're trying to prove. So here I summarize these two things, and then here's the beginning of the proof. So we start with the xn. If we want to show a function is continuous, that means for an arbitrary sequence, we have the plot property that was described in an earlier slide. So we start with an arbitrary sequence that approaches arbitrary value a. Then we need to show the sequence f of xn plus g of xn, which you plug it into this function that we're trying to show is continuous. Right here, this needs to converge to something, that function value, which is fa plus ga. So given an arbitrary sequence, we need to show this property. Then we're done, because that's our definition, which is equivalent to so-called epsilon delta definition. So we have this property f of xn approaches f of a, g of xn approaches g of a because they are assumed to be continuous. So here's a neat little trick that I use, and most of the book uses like add and subtract trick, but from teaching that thing, and many students find it is difficult to understand what's going on, so I find this is more reasonable approach. So we define alpha n to be the difference between these two quantities, fxn minus fa. Because we know they're continuous, that approaches f of a, it's obvious that f of xn minus f of a approaches 0. This doesn't use, we assume it's continuous, though, so that I think we can accept that this continuously approaches f of a there in the 0. The same thing, g of xn approaches g of a, makes this g of xn minus g of a approaches 0, because g of x is assumed to be continuous. And we call that quantity beta n. So if you solve for this and f of xn and g of xn, we have this thing here. So we can kind of broke this function values and as a sum of two things. That's the main technique. It often happens a lot in analysis. So what we're doing next is we're comparing these two quantities. This is what we want to show, f of xn plus g of xn. How far is it off from the f of h plus g of a? So we have this function value, and this is where we think it's approaching. So we measure the difference and hope that approaches 0. So eventually we use something called squeeze theorem. So what I did next is that I replaced this f of xn, g of xn, with this, what we have found here, in terms of alpha n and beta n. So that f of xn becomes alpha n plus f of a. G of xn becomes beta n plus g of a, like we have found here. That nice thing happens is f of a and g of a, as the sum of two things, cancel nicely with f of a plus g of a right there. So inside nicely simplifies to alpha n plus beta n. Alright, so watch out, these were exactly equal, and the next part was exactly equal. Now, it's not exactly equal. This is called triangle inequality, that alpha n and beta n, it doesn't have to be positive, it could be negative, but what you are looking at here is that if I turn that alpha n to a positive number, turn that beta n to a positive number by putting an absolute value around it, then add it, then it's going to be two positive number, and if you compare it with that, if these were both positive numbers, it's going to be the same thing. If the one of the number is not positive, negative, and the other one the positive, you can see that's a cancellation. So its magnitude of the number whole thing is kind of getting smaller. But on the other side here, because we changed everything to a positive, there's no cancellation. So this magnitude of this number right there is always bigger than that one. So in the vector form, this looks like what is happening to the size of a triangle. So this is often called the triangle inequality. But if you just play with this couple of numbers, positive, negative, and negative, negative, and positive, positive, this is not hard to understand. And this quantity makes it a little bit bigger, but this is good enough approximation to conclude something very rigorously. So when I use approximation, we're not really being sloppy here. This is approximation is good enough for a rigorous argument. So this exact quantity, alpha n plus beta n, is less than or equal to these two positive number. And what happens here, this is our fundamental lemma, because alpha n and beta n approaches 0, absolute value of alpha n and absolute value of beta n approaches 0. So the first item of that fundamental lemma we looked at, if these two tiny quantities approaching 0, the sum must approach 0, and in that proof we didn't use continuity. And that's the whole purpose of this lecture. So therefore from that lemma we know it approaches 0. This quantity we wanted to examine is trapped in between 0 and this quantity that eventually approaches 0. So what could happen to that? By squeeze theorem, that quantity approaches 0, and that's the proof. That's the proof of why this f of xn plus g of xn approaches this number f of xa plus g of a, f of a plus g of a. And that we established this fact, not using any particular property of xn, but only the property that it approaches this base number a. So therefore, it fits into our definition. So that's the proof that f of x and g of x is continuous at every point, therefore it's continuous. So with that example, we pretty much explained everything about that I planned to, but I'm showing one more example that involves a little bit more of a thing. So I use these two line segments juxtaposed together to show you intuitively, to explain what we mean by f of x plus g of x is continuous. Now, if you try to do the same geometric trick to this f of x and g of x, f of x times g of x, it requires a little bit of work. And it is really fun to do that process. And you yourself, and you challenge yourself, how am I going to draw, the product of two number line segment that is given without using calculators. Just draw things around here with a ruler and then other stuff that doesn't have any marks on it and stuff like that. So that's again, from there you might understood discontinuity and naturally, but definitely not by looking at the decimals, because if we multiply two numbers and then the behavior of decimal is not easy to understand. I did it myself, really. So if you're not using the geometry, and because that in it we all assume this continuity built in there, so we have to avoid that. And next approach would be looking at the decimals and conclude something, and multiplying and predicting what is happening to the decimal level is really, really tricky. So here's a proof. Like we did to the addition part, we start with an arbitrary sequence that approaches a. Then we write alpha n as a difference of f of xn and f of a, therefore it approaches 0. It follows from the property of a continuity we're assuming, which is not written here. Same thing, beta n is the difference of g of xn and g of a, and that's supposed to approach 0. And what we want to show is that f of xn, g of xn, approaches f of a times g of a. So we measure the difference, and we use triangle inequalities and stuff like that. So let's see what we do. Alright, I've kind of skipped one step, but it was written in an earlier step, so I'm just going to explain. What is shown here is f of xn and g of xn, and we have this alpha n and beta n there, so we're going to solve this one for f of xn, and g of xn, you can see f of a is added to both sides, so f of xn is alpha n plus fa, which is shown here. The same thing, g of xn is a beta n plus g of a, so that's written here. So that f of xn times g of xn is replaced by this thing. Then we're going to expand this. So if you expand it, then we have alpha n times beta n that showed up here. Then fa times beta n, that was showed up here. And alpha n times g of a, that showed up here. And there are 4 terms, so fa and g of a showed up there, but that cancels with this fa ga. So that's why we have these 3 terms. Now it's time to use the triangle inequality again. These are quantities, and no matter there's a positive or negative, if we switch all 3 quantities to positive like this, we make this quantity necessarily bigger. That's what's argued before. So here alpha n, put absolute value. Then the second term, put absolute value there. Third term, g of a, alpha n, and put absolute value there. So if you believe this alpha n times beta n approaches 0, and this one approaches 0, that one approaches 0, the first item of our fundamental lemma again tells you this whole thing approaches 0. Therefore, whatever is sandwiched here approaches 0. But to make this last bit a little bit more rigorous, I'm going to do something about this term. These terms are okay. This is where we use that second item of a lemma too. See if I can show you that one, the lemma there. So I'm back to this lemma. So we used this a couple of times in the earlier statement. We're about to use this one. Constant times an is going to approach 0 if an approaches 0. All right. So that's something we're going to use here. So let's see. So we're back to this. And here fa is a constant and beta n is multiplied and beta n approaches 0. g of a is constant and alpha n is approaching 0 is multiplied. So we're going to use that number 2 item from the lemma for these two terms. But that one is different, so we're going to do something about it. So here's how it goes. Alright, let's compare. Next line. This term fa and beta n and ga alpha n appeared exactly. But this one changed, but it's not equals, it's greater than equal to. So let's compare what happened to the beta n. And I wrote here, if n is large enough, and this is supposed to be beta n is a typo. Sorry about that, but either way. If n is large enough, because we know alpha n approaches 0, it is absolutely correct statement. If n is at some point eventually alpha n is very, very close to 0, so it's safe to assume it's less than 1. So one of the factor here is less than 1, so that's why this factor is replaced by 1 then appeared here. So if I change that to the beta n, still correct statement because beta n approaches 0, we have the statement. Then this falls into the fundamental lemma that I showed it again. Alpha n approaches 0. Item 2, constant times one thing approaches 0, and constant time one thing approaches 0. Therefore, this approaches 0, the whole thing. So that quantity approaches 0. So that's the end of the proof of this. So here it shows that product is also a continuous operation. That's pretty much what it is showing. So let me summarize you. What we wanted to define is this notion of continuity. And to do that, we had to use this idea of f of x approaching xa, the values around that. This is written here, values around x equals a. And in that notion, this x approaching a needs to be clarified. And we wanted to avoid the continuity to property of continuity when we define this notion of x approaching a. For that, we use this sequence of xn approaching a instead of a value of x continuously approaching from the left or right. Nothing like that is along the sequence. But in most of the textbook, they use this idea of approaching from the left and right to kind of help the student to understand the notion of the continuity, but logically, for the foundation of rigorous development of a mathematical idea, this must be the approach. So that was the whole purpose of the lecture, with some technical exercise in it. But thank you for listening.